Hey everybody, last video of the day, so let's go ahead and start talking about it. Right now we're going to be talking about emulsion polymerization. Now emulsion polymerizations look very similar to bulk, with a few differences. With emulsion polymerization, you've got monomer, you've got initiator, once again being a radical, you have a non-solvent, and a surfactant. That's what makes this different. Or honestly, it's a fancy word for a soap. Now, to remind you what this looks like, here's the traditional look of a surfactant. So, you've got a polar head and a non-polar tail. You could also describe this as a hydrophilic head and a hydrophobic tail. How does this work? Well, quick reminder of how surfactants work. Let's take a look at, say this. You can clearly see where this group is polar and hydrophilic, and this group is hydrophobic. So why? Why is this important to you? Well, let's take a look. When you put surfactants in water, there's a bunch of interesting things that happen, and they all depend on concentration of the surfactant. Okay? So let's take a look. How this operates is, let's say you have low concentration of surfactant. Well, in that case, what tends to happen is your water is there, and let's make the surfactant red. The polar head is on the water, on the surface, and you've got those hydrophobic tails sticking straight out, or honestly probably lying down, but there's a little bit of mobility there. What this is this is why ceramic tubs with soap water are so damn slippery, is because you are essentially stepping on grease when you do that. What about a medium level of surfactant? Well, in a medium level of surfactant with agitation, meaning we're stirring it really well, you end up with something that looks like this. This is a fancy word. It's a micelle. And if you're thinking to yourself, self, that looks an awful lot like a droplet from suspension polymerization, you're not entirely wrong. Okay, so what we've got going on here is the micelle is spherical in shape. All the hydrophilic ends are on the surface wanting to be next to the water. All the hydrophilic ends are all saying eep and hiding on the inside of the micelle. What is surprising is the amount of void space inside of that micelle. Now, just to finish out the thought, we're going to come back to micelles in a minute. How about high concentrations of surfactant? Well, in those cases, what you get is this. Oh, sorry, I'm using the wrong color. I use red for surfactants. Look at me, I'm paying attention. With the polar head group facing outward and the hydrophobic tails in the middle, this is a bilayer, which looks a lot like the lipid bilayer that encompasses our cells. So, what I want to point out to you here is this. I have grossly oversimplified what happens with my cells and what happens with surfactants in water. Folks, anyone who knows what they're doing would probably spit on my neck for what I've said here. But I think for our purposes, it will be just fine. So in a polymerization like this, here's what we have. All right, guys, I don't know when this kicked off, so I'm going to assume it was on this page. Occasionally, this program likes to shut down for reasons that I cannot fathom. I apologize. Hopefully, this will make some degree of sense. So if we take a look at this micelle, what we've got is the micelle itself, the circle, the hydrophilic heads at the outside, the hydrophilic tails pointing in. Monomer can migrate into those, in between those tails, because monomers are by and large hydrophobic. All that has to happen now is our initiator coming in there and starting off the polymerization. So the question you should probably ask yourself is, why, God, why? Why is this happening? Why is this important? Well, knowing the following things. The concentration of your surfactant. Agitation rate, or how quickly this is stirring. Knowing the temperature of the water. Knowing external pressure. There are a bunch of other factors that go into this, kind of like it did for the determination of the size of the droplets for suspension polymerization. But knowing all of these things, you can tightly control micelle size. And if you know the size of your micelle, you have a really good idea of what the maximum molecular weight of the polymer will be in there. This is a good way to control the dispersity. Of the chains. All right? Now, I'll be honest with you. I've been doing polymer chemistry since 1992. That's when I first took my polymer chemistry course at my undergraduate, Western Kentucky University. Go Hilltoppers. And even then, I had trouble understanding the point of emulsion polymerization. I just don't get it. Now, that me not understanding it does not affect at all that just because I don't understand it doesn't mean it's not important. Sorry, I had a phone call. They wanted to talk to me about my extended warranty. So, the paint industry, coatings, cosmetics. Just to name a few. This in total is a high billion-dollar set of industries. All of them use emulsion polymerization for what they do. Now, for me personally, once you have to get into all of these that go into making that important, my eyes blur and go out and I don't really understand it. So, these are, how do you get your monomer, your high polymer outside of that droplet? Well, from micelle. Well, once the polymer hits the size, it'll burst out and precipitate. Or you can do something to invert the micelle, which usually means putting it into a hydrophobic environment. All right. These are the 4 types of polymerization that we have talked about today. This is what today's lecture was going to be. So I will take questions for all of these on Friday, and I hope everyone has a good day, and I'll see you later on in the week.